Okay, so this slide is supposed to give us a little heads up of when we use absolute values and when we don't, when we're using square roots and cube roots. So this will come up towards the end of the lesson again, okay? But first of all, 2 cubed. You have a reference sheet. I gave you a reference sheet. So if you don't remember your cubes, what is 2 cubed on the reference sheet? What is negative 2 cubed? Careful, look on the reference sheet. It's negative 8. And again, it's just negative 2 times negative 2 times negative 2. What about 4 to the 5th? On your reference sheet? Careful, 4 to the 5th power. 1,024. And then what about negative 4 to the 5th?
Negative 1,024.
Exactly, negative 1,024. And the takeaway from that, the thing that I want you to remember for today's lesson, from cube or raise something to the 5th power or any odd exponent, whatever the base was, that'll be the same sign as your answer. So example, 2 cubed. 2 is positive, and so is 8. Negative 2 cubed. Well, negative 2 was negative, and so is your answer, negative 8. That's always true. And that will be important when we talk about roots later. The second thing we're reviewing has to do with the even exponents, or even doing our square roots and our cube roots and fourth roots. So 3 squared. 3 squared, 9. Negative 3 squared is also 9. And important when we start thinking about our principal roots, which we'll talk about in a little while. The 3 and the negative 3, both, when you square them, give you 9. That'll be important. What about 5 to the 4th? Good. 625. And what about negative 5 to the 4th? It's also 625. So the takeaway here is regardless of the sign of the base, when you raise something to an even exponent, it always comes out positive. Okay? All right, so now to your notes. First, the definition of a square root or a cube root or a fourth root or whatever root called nth root is down here in that key concept box. For any real numbers a and b, then a is an nth root of b. They've got an example, but let's use one that we already did. 3 squared is 9. Therefore, 3 is a square root of 9. What is negative 3 squared? It's also 9. Therefore, negative 3 is also a square root of 9. For example, negative 3 to the 4th is 81. So negative 3 is a fourth root of 81. 3 to the 4th is also 81, which makes 3 also a fourth root of 81 by definition. There's a couple other words that we're going to use, as you can see in this diagram. We've used the word index, kind of, the n right here. Well, in the example up here that they gave us, the fourth root would look like this, the fourth root of 81. Well, we'd have to choose between the 3 and the negative later. Then there's the 81 itself, called radicand. You're going to hear me use that a lot. And the word radicand, just think stuff under the... Like on the board over there, there's a 25 and an x squared under the radical. So 25x squared is the radical. I'm sorry, is the radicand. And then last, the radical sign itself. Let's get into it. Example 1. What are the square roots of each of them? According to the definition, when it's asking what are the square roots of 4, it's asking you what could you square to get 4? 2, 4, or negative 2. So there's 2 answers. 2, 2. 5. You could, so it's asking what are the square roots? You could square a 5 or a negative 5. What about 64? 8 and negative 8. What about 100? 10 and negative 10. Good. Then we switch gears. questions 5, 6, 7, and evidently I can't skip number 8, but 5, 6, 7, and 9. What are the cube roots of 8, which we may not be as familiar with, so look. Cube roots are 2, -2, 3, and -3. Now, do you notice something about the square roots versus the cube roots? Yeah, there's only one answer for all the cube roots, but there's two for the square roots, which brings up an issue called principal root. Because back in 7th grade, or whenever it is that you were first kind of exposed to this, if someone asked you the next question, number 10, what's the square root of 4? Your automatic response would have been 1. 2, well, tell me why you didn't put the -2 that we said in number 1. Well, the reason that you didn't is because you were taught the principal root. The definition of principal root is just the positive one. All right, the technical definition is the non-negative root. Principal roots only apply for even indices. In other words, square roots, or fourth roots, or sixth roots. Okay? Why is that? Because there's not a choice for cube roots. The principal root of cube root is that it is. The root of 8 is 2. There's not choices. Make sense? All right, so the square root of 4 is what it was. Square root of 25, the non. Square root of 64, 8. Now careful, square root of -25. If you look on your list, there's nothing that will multiply by itself and give you -25. This goes back to what we knew before. You can't have a negative under square root. So it would have been an I answer if we wanted to use I. But in this unit, we're going to stay with no real root. Now, how would you know the difference between should you circle an answer no real root versus circling 5i, which we also know is the real answer, not the real answer, but the imaginary answer, 5i? Look at your choices. If they have 5i as a choice, that's what the answer they're looking for. If they have no real solution, that's what they're looking for. They won't have both, okay? But I get how that can be confusing since you already know what I is. All right, and last, cube roots. Cube root of 8. What's the cube root of 8? What would you cube to get 8? 2. And there's no choices, it's just 2. What about the cube root of -8? It's not no real solution, it's not no real root, because you look at your number 6, and you said you could cube a -2, which means you can have negatives under a cube root. So your answer here is -2. Cube root of 27. 3, and cube root of -27. Yeah. All right, so that's all numbers. There weren't any variables in any of those problems. It gets a little more confusing with variables, but the first time we go through this next page, we're not going to think about absolute values once. Okay? We're going to answer every question without absolute values. Then we'll come back and talk about them. And the reason we're even going to have to talk about absolute values is because in number 10 here, you said the square root of 4 is 2. And not -2. Agree? But you use a variable, and we'll go ahead and look at the next page. Keeping that in mind, square root of 4, you're supposed to write 2, right? Let's think about that as we answer number 18, and then we won't talk about absolute values anymore, okay? The square root of x squared is what? It's x. The square root of x squared is x. Now, just like the square root of 4 is supposed to be 2, you have to promise or guarantee that what you just wrote, what you just put down there is x. So sure that's 2 and not a -2. That's what we'll need to talk about later, but not now. Okay? All right, so let's number 19. X squared. Great, x squared. And for those that are still looking at it thinking, what do? Well, you try to make as many squares out of x to the 4th as you can. So you can make not 1 x squared, but 2 x squareds, each of which reduce. And since we've done this in a previous unit, you understand that's the square root of x squared times the square root of x squared, which is x times x. Or, final answer, x squared. What about number 20, though? how many x squareds can you make out of x cubed? You can make one of them, but that doesn't take care of all the x's.
Would it be x on the outside and then another x?
Exactly. You've got x squared and you've got a over x. So like you said, that first x squared is going to reduce to x on the outside. But that second x, and exactly what you see there, crossing out the x squared, circling the x, that's what you'll see in my notes. That's what you'll see in my homework keys. Straight. If I crossed it out, that x is coming out. If I circled it, like you said, Harley, that x is staying under the radical. So final answer, x squared roots of x. Okay. Next one, x to the sixth. How many x squareds can you make? 1, 2, yep, 3. Perfect. So when you reduce each one, how many x's come out? X to the third. And this isn't too bad, is it? So let's keep going. We got to switch our mind a little bit. Because if you look at 22 through 25, what do you see? Yeah, the index changed to 3, so we've got cube roots now. So your mind's got to switch. I'm not looking for perfect anymore. I'm looking for perfect cubes. So what is the cube root of y cubed? Y. Good. What about the cube root of y to the 6? Again, your mind is switched. You're not looking for squares anymore. You can make this into y cubed times y cubed, but that's all of them you can make. So how many y's will cancel? 1, 2, not cancel, that's the wrong word. How many y's will come out, or what's the cube root of y cubed? The cube root of y cubed squared. You'll probably come up with a pattern if you haven't already. Yeah, kind of a divided pattern, which will 9 when we start dealing with rational exponents. Your whole division little trick, if you will work, and you'll know why in Learning Target 5. You'll be like, oh, okay, that's why that works. Okay. But next one, how many y cubes can you make out of y to the 9th? You can make 1, 2, 3. Yeah. So each one reduces to y. It's the cube root of y cubed each time. Becomes y times y times y cubed. Good. All right, and then the last one, if you're thinking shortcut, you're thinking division by now, right? All right, so here's the way, if you want to shortcut this, what would you cube to make y to the 24th? You would cube, oops, wanted to use a different color there, y to the 8th. So essentially the cube root and that cube will reduce, and you're left with y to the 8th. Or if you would like, you can write the cube root of y cubed, y cubed, y cubed, y cubed, y cubed 8 times and cancel each one. But you're starting to get the pattern, right? All right, so let's see if we can see. It would sound like an echo, wouldn't it? So let's see if we can speed this up a little bit. 26. X times y. Yep, good. 27. Ooh, got a little slow down here on this one, right, because of that y cubed. Let's see, we can make x squared stay x squared so that we've got a perfect square there. Y squared can, you got one y squared and a leftover y. So two things are coming out. Exactly. The x that we reduce, square root of x squared, that x comes out. The square root of y squared, that y comes out. But the y that I circled is stuck. So the final answer, x times y, square root of y. Again, we're going to need to come back on most of these and talk about it. This is the first run through. Number 28, how many x squareds can you make out of that? 2. How many y squareds can you make? 2, but is that enough? No, you need one more y, don't you? So when you reduce, you have 2 x's, 2 y's, and you have 1 y that's staying under the radical. So, final answer. X squared, y squared, yep.
And another y.
And another y, but where at? Under the radical. That last y, it's kind of stuck under the square root, if you will. Okay? because it does not reduce. A to the 5th, B to the 6th. That's A squared times A squared times A. And then how many B squareds can we make? 3 of them. All right, I got to work on my penmanship here with this airliner. 1, 2, 3, 4. 5 things are reducing. Is anything staying? Is anything not reducing?
Yeah.
Yeah, that 1A. So final answer would be A squared, B cubed, square root of A. Awesome. Awesome. All right, now if we can, we're going to try to skip writing those steps now because we're going to envision them. What's the square root? Next problem. What's the square root of 16? You have a choice. You're telling me 4, not negative 4, right? Okay, that's fine. And then what about the square root of x to the 4th? X squared. Good. Square root of 25, you have a choice, and what are you going to tell me? You're going to tell me 5, the principal root. And then you're going to tell me x. Good. Square root of 100? 10. A squared, yes. And what about the b? How many b squareds could you make out of 10 b's? You can make 5, so it'll be b to the 5th. All right, slow down now. Cube root, not square root, cube root. The next problem is a cube root. So you look at your red, you don't remember your cubes. The cube root of 125 is a nice number, it's 5. And the cube root of x cubed is x. And 34, we're staying with cube roots. So be 6. Be careful. Now, I'll write this above here. How many cube roots can we make? I'm sorry, how many cubes can we make out of m to the 6? M to the 3 times m to the 3. That's it. So 2 m's are coming out, right? Have you come up with a little shortcut in your head yet?
Yeah.
You're taking the exponent 6 and dividing by the index 3. That'll work because of learning target 5. When we do a rational exponent, you'll completely understand why that works. Okay? And you can do the same with n to the 9th. N to the 9 divided by 3, so n to the 3. 4th root, so I'm going to go back to the black ink pen because it's an index. 4th root of 81, I made this mistake doing the homework. I wrote 9 on the homework one time because it's just tempting. You see 81, you see a square root looking sign. It's a 4th root though. So the 4th root of 81 is 3. And the 4th root of x to the 4th? X. 4th root of 625, another good number. 5. Again, you had a choice. You're telling me the positive version, right? Okay. And a to the 8th, how many a's? A squared. B, and last one. The 5th root can have a negative, yes, because it's odd. And then if you look at the chart, your reference sheet there, there's only one number that you raise to the 5th power and get negative 243. It's negative 3. So negative 3. How many b to the 5ths can you make out of b to the 10th? B squared. C to the 6th. All right, so now let's just take a moment. Look back through that page. Was that too bad? No, that wasn't bad. I thought that was pretty easy, right? Okay, and as promised, the first part of the lesson is pretty intuitive, pretty straightforward, not too bad. But also as promised, the second part, what we're about to do next, pretty confusing, okay? So I need your active listening ears now. I need your attention. I need your, looking, listening, asking questions. That's right. Bend those ears forward if you have to, whatever it takes. But stay engaged, okay? All right. Ask questions, though, okay, because it will be confusing. All right, so here we go. The good news, the first thing is, the reason we need absolute values is for principal roots. We need to make sure that we write down a positive answer for every even index, which is good news because we don't have to worry about absolute values for odd indices. So anything that's in blue on the screen, those were odd roots. We don't have to think about absolute values for those problems. Okay? We never think about that. And the reason is, without going into too much explanation, if an odd index, if its radicand is negative, then the root will be negative. It'll work itself out. If it's supposed to be positive, it'll work out to be positive at the time. But let's take a look at number 18 and talk about that square root of 4 and that square root of x squared. If I asked you the square root of 4, you'd say 2. Not negative 2, you'd say 2. In number 18, could x be negative 2?
Yeah.
It could, because what happens when you square a negative 2? You get a 4. So the radicand could be 4, and that x squared could be hiding, if you will. It could be hiding a negative 2. So when you write x as your answer, you could be writing that negative 2 as your answer. So the way you make sure that you're not, you put absolute values around it. So it'd be absolute value of x, exactly. So we take 2 bars around the x. All right, now each question is going to present more and more things to think about. Okay, number 2, x to the 4th. X to the 4th, we talked about it in the 1. All even exponents are going to be positive. Radical positive. Has to be. The question is, could x itself be negative? Yeah, it could. It could. You're right. Negative, does x squared, is it guaranteed to be positive? It is. That's good. It's a good catch. Why? Because it's a squared. So basically, a squared will take care of that negative issue. So we don't have to do anything on number 2. Exactly. That's perfect. Great. Great. Number 20. The square root of the given information is giving us more than just a square root sign and an x and a 3. It's telling you, if you didn't write the answer no real solution or no real root, then you're assuming something. And what are you assuming? You're assuming that the radicand's positive. Otherwise, what would you put? If that had said, number 20, square root of negative something, you'd have said no real answer, but you didn't, right? So we had to assume x cubed is positive. What's the only way that that happens? If x is also positive. Do you agree with that logic? The square root of x cubed, number 20, x cubed has to be positive, or you can't do the problem without saying no real solution or no real root. Which means you can further conclude that x itself was positive. That makes sense. So, x is positive. We don't need any absolute values. Confusing, right? I'm getting those looks. I'm starting to get those. All right, number 21. Let's get it. X to the 6th. Let me give you an example on this one. All right, let's put a number out there. Let's pretend x is negative 2. So negative 2 to the 6th, 64. Number 21, that x to the 6th, that's the radicand, could be 64. Furthermore, x itself could be negative 2. We just saw that. So when we write x to the 3rd, what are we really writing? 2 to the 3rd, which is negative 8. So it needs absolute values. Right, and the square root answer can't be negative because of the same reason when I ask you for square root of 4, you say 2. The principal root, the non-negative root, the positive root. So this one needs absolute values. All right, this is probably too early to tell you this, but I'm going to go ahead and give you the thing that I despise the most in math, and that's the blanket statement that works every time, but you don't know why it works. Okay? We've just talked about 4 examples of why it works, so here's that statement. You might want to write this down at the bottom of your notes. The very, very bottom of your notes, on the back page, towards the very bottom, it talks about, as a general rule, absolute value will only be used for even indices. All right, next to that, you want to add something. It's kind of a 3-part criterion. Part 1. I have room, but I'll try. I made room. If even and part 2. Radicands three criterion are met, you have an even root, you have an even exponent under that radical, and when you simplify it, exponent, then you need absolute values on that variable. So you need absolute values. Let's go back to one that actually uses this and see if that works. 21. Number 21. It was a square root, right? Which means its index is 2. The exponent is 6 in the radicand, right? The answer was x cubed, which was an odd exponent. Has 3 checks that met all 3 criteria, which means you need absolute values on the x cubed. Now, we're not going to just memorize those 3 criterion and let it work for us. We're going to keep talking about this as the homework comes up, talk about why it works, because that's the problem with mathematics is sometimes people just try to memorize all these little rules that just magically work, and then they think math is a bunch of disconnected ideas that well, they don't connect, but they do, okay? But I do want you to know that that's available to you, that little checklist can help you out while you're learning this, okay? So let's use the checklist on number 26 through 29, and then we'll call it a day. We'll finish the notes the next time we come in. We'll do some homework together, but we'll close the video off and go from there. So 26, using our checklist. First, is it an even x square root? The x squared, was it an even exponent? Yeah. Did it come out as an odd exponent, x to the 1? Yes, it did, x to the 1, right? X to the 1. So x needs values. Before you put them, let's move on to y. It was an even index. Is y squared an even exponent? Check number 2. When you simplified that, did the y have an odd exponent? Check number 3, which means they both need absolute values. So you put the absolute values around both of them, x and y. 27. Even index? Check. The x to the second, is that even? Did it come out odd? Then x needs absolute values. The y, is it an even exponent? No. The y cubed is an odd, which means it fails the second check point. So it doesn't need absolute values. All right, but I don't want that just to be all we talk about. So let's talk about it. If x squared is right there, what does x squared have to be? Positive or negative? You tell me, when you square a number,
Positive.
it's positive. You also know that the radicand of a square root, all the stuff put together has to be positive, right? So what does that force y cubed to be? It forces y cubed to be positive, which forces y itself to be positive. The only way you cube a number and get a positive is if the number that you started with was positive. So you see that line of thought? The first thought was the whole radicand. Second thought was x squared is always going to be positive. And the third thought was, well, if x squared is positive, that forces y cubed to be positive. And the final thought, if y cubed has to be positive, y itself was positive. Okay, now why is x not necessarily positive? Because you could square a negative number and still make x squared positive. So in other words, the way I think of it is x squared could be hiding a negative. Y cubed can't be hiding a negative, because if it is a negative, the y cubed will be negative and expose the whole negative. So it's confusing, okay? But that's why. Now, our statement works, but that's why. 2 more, 28. X to the 4th. Even index, even exponent, but what did it come out as? X squared. Y to the 5th. Is that even? Y to the 5th. No, so y doesn't need them for the same reason as 27. X to the 4th is guaranteed to be positive, which forces y to the 5th to be positive. Furthermore, forcing y to be positive. Okay, last one, 29. B to the 6th has to be positive no matter positive or negative, which in my terminology, B could be hiding a negative. Okay? It's an even index, even exponent. It came out as a b cubed. It needs absolute values. What about the a squared? Well, it wouldn't need them even if a could be negative. But can a be negative in this problem? Well, b to the 6th has to be positive regardless of what b is. Forcing a to the 5th to be positive, forcing a to be positive. So a doesn't need them. All right, so we're going to stop the recording right here, because if you do need to go listen to this, that's all you, okay?